it generates like a CSV document of all the links that.
What do you do it through? What do you do it through?
Trying to find how universities talk about AI.
Right, what do you, what's great through?
Okay, let's get started. We got everybody? Close enough. I want to start by talking about the homework. So this first problem is on GDP, or more specifically, economic growth estimates. As we saw in the paper for it, United States, most other countries, actually measures this in two different and mostly unrelated ways. But they're related in the sense they're both trying to measure the same thing. But they use different inputs and they study different methods. And the main thing to keep in mind here from a perspective of social science is that what we call economic growth data is actually the output of an economic growth model that the government uses. So neither the United States nor any other country actually counts the value of all transactions in a quarter. That would be way too much work and too onerous requirements for reporting and everything else. So this is actually a model, and OECD countries, including the United States, have some standards that they follow that are actually fairly transparent about what the model is and what preliminary data and stuff they put into that model. But it's still a model. It's a model created by economists. And that certainly raises the question from like Fisher's perspective, how or why are we supposed to be completely objective about something that human beings created, like an economic model for growth? So Fisher, who, as we said before, was an agricultural experimenter. His view on science was essentially limited to crops. And you can understand how someone who like spends their day looking at corn stalks or wheat plants or something like that would trick themselves into thinking that data is objective and anything human, is potentially subjective. So if you're doing agriculture experiments, you're like, how big does this plant grow? How long does it live? How much corn does it produce? If we give it different fertilizer or whatever, like what's the treatment effect of that? You can sort of see how someone whose exposure to science was limited in that way would think of data as being from nature. But Fisher, at the time, mostly 1920s, social science hadn't been invented yet as like academic departments or whatever. That didn't really come until starting in the late 1940s at the earliest. And so one of the things that makes social science different from other sorts of science is that most of the things we call data in social science are not actually from nature, or at least not directly. The data that social scientists produce and analyze and governments like collect and whatnot is actually at least as subjective or comparably as subjective as our beliefs about the parameters that go into that model are. So there's all kinds of social science stuff that uses, like, as one of the predictive variables, democracy. Well, some human or army of graduate assistants of a human professor had to make value judgments as to like how much this or that country is or is not democratic or whatever in order to give them a score. But that's something that is considerably more subjective than how many ears of corn are on this plant. And so, you know, economic growth, like most of the things in social science, you know, our data are subjective. And that's where a lot of the scientific debates come around. And so there's no real clear distinction between objective and subjective to be found in social science, which makes Fisher's insistence that we only do this, you know, objective things that we can deduce without any sort of human beliefs about it, especially problematic for the use of social science. Now, that's not entirely Fisher's fault, because at the time social science didn't exist, but it is certainly the fault of a lot of people around 1950 who, when social science was being started out, uncritically accepted what Fisher said implicitly or explicitly about plants, and then just imported it directly for the study of things pertaining to humans, or creations of humans, or data produced by humans, that sort of thing. Another thing to bear in mind about this is, or this particular thing with the way you see this reported in newspapers and stuff like that, like newspapers will say the government reported that GDP was 3.3% in the last quarter of 2024. Well, that's not really what the government said. The government said it estimated growth to be 3.3 or whatever. And, you know, newspapers and stuff like that selectively ignore a lot of other things the government said, which was including which, we estimated it to be 3.3, but we're going to be revising it 5 times. It comes from a model rather than, you know, something that we counted like the census. Even the census is like, it's intended to be a count, but it's not really a super accurate count. Well, it is very accurate, you know, plus or minus 1 million. But anyway, we don't count economic transactions. So this is coming from a model. And that model was created long before the pandemic. And the pandemic seemed to screw everything up. So we're not even totally sure how reliable that pre-pandemic model is for during pandemic and recovery from pandemic and possibly new normal after pandemic, after-ish pandemic, in terms of more people working from home and, you know, all that. So, okay, government says that, it doesn't get reported in the newspaper, it gets reported in the newspaper, the government said this. Moreover, the government said, okay, this is 3.3 if we measure it on the expenditure side. But that's going to be somewhat inconsistent with an equally valid measure on the income side that we haven't reported yet. But in the past couple of years, gross domestic income, GDI growth, has been considerably less than GDP growth, even though they're ostensibly measuring the same thing, or measuring would be a strong word, model in order to measure the same thing. So all those caveats don't get reported in the newspapers and stuff, which is unfortunate, although newspapers perhaps correctly infer that the readers of those newspapers can't handle if they got into any nuance about the uncertainty of these sort of things. So, the newspaper doesn't feel like they can say, well, they estimated it to be 3.3, but that estimate has a standard deviation of 0.7. So this is really only accurate to like one decimal place to the left of the decimal point, sort of deal. And so you could see that with sigma, it comes out to be about 0.7. So that's one, we don't know what the truth is. But if we did know the truth, our estimate of the truth would have measurement error with a standard deviation of 0.7, even though a typical value is like 2 or 3. So the measurement error is rather large compared to the truth and compared to the variation in the truth. But, you can certainly choose an S here that gives you a high correlation between the draws of P and I. It's not actually sensitive to M, but you should choose M to be something that is historically reasonable. I think a lot of people were choosing big values of M, in which case, okay, you still maybe get the right correlation, but your economic growth expectation would be more appropriate for like a developing country. Whereas United States and Europe have been closer to 2% for most of your lifetime. And then, okay, so in January, they came out with preliminary estimate. It's reported as 3.3, so 1 decimal place of accuracy, even though the decimal place of accuracy is not particularly accurate. But if we condition on the draws being between 3.2 and 3.3, we get something that looks like this. So in black, we have the PDF of mu, and in red, we have the PDF for I. So this is something that is very important in general when thinking about Bayesian and stuff. So we can have beliefs about the truth in black, but our data has additional, in this case, data on GDI, will have additional measurement error on top of the truth. So one, we're not totally certain what mu is, although we have a decent idea about it based on the GDP release. But even if we knew the truth, we wouldn't know exactly what GDI would come out as until it happens, because GDI comes from the model and incomplete data and all sorts of things like that. So our beliefs about what GDI estimate will be have heavier tails, more variability to them. And that's going to happen with pretty much any model, that your estimates of the parameters are going to be more concentrated than your predictions of the data that are ostensibly a function of those parameters, even though GDI is a relatively simple function of this in a measurement model. So the second estimate comes out, that happened yesterday. That was like 3.2. So you could think about using what you had before to make a prior for the second release, in which case, it might have a mean and standard deviation, something like that. Make P be 3.2, and then you have a prior on mu, and then you have a likelihood function of mu to be evaluated at the known data P. And then it's not exactly how I would do it, because the second estimate of P is not independent of the first estimate of P, but this is all close enough. The process of it, you integrate the numerator to get the denominator, and then you plot this in ggplot. You get something like this for the distribution of your beliefs about mu given the second estimate of GDP. Now, probably if I was doing this for real, I would just say, pretend the first estimate never happened, go back to your original prior in January or whatever, and then just condition on the second one. But anyway, the process of it made sense. We have this, which is going to have an area of 1 under it because we normalized it correctly. For our beliefs about what growth was last quarter, given the second estimate of GDP growth. And you can see, yeah, it's centered like a little bit above 3. Sure. But we are still considerably uncertain about exactly what it is.
It's a little more long-winded way, but could you still like redraw from a like a d-norm function, like recreate a likelihood in a prior, and then like marginalizing over it by just dividing it by like a normalizing constant?
Well, the normalizing constant needs to be specifically that number.
Yeah.
In which case, this will integrate to 1.
Yep.
And so I think maybe that could have sounded right. But however you did it, you're basically saying, well, you know, the center of this thing is a little bit 3.1-ish. But it could be as low as 2. It could be greater than 4. There's a little bit of chance there. It could certainly be anywhere in the 3-ish range. And that amount of nuance is not really captured in the press release or the economic reporting surrounding these things. And given how important the level of growth or the rate of growth is in the United States or any similarly sized economy, China as well, given how important this is, lots of stuff is being decided on the basis of it when we don't know what it is that well. Just given like one piece of data. When GDI comes out, we'll have more information with which to update all this. But we have like a fundamental kind of non-negligible amount of uncertainty as to what something was in the past. And that's just the way it is. But when you see it reported in like newspapers and stuff, it's kind of weird. Like if you were reading them in January, it would say like, economists expect economic growth last quarter to be 1.8%. Well, that's not even accurate. Like any two economists are not going to agree on anything. Really what the newspaper did a survey of economists and the average was 1.8%. The standard deviation, they don't even say what it is, but it would not be 0. But okay, economists predict it's 1.8%. And then then the release happens 8:30, and by 8:31 there's already a story on the New York Times saying, no, it was 3.3%. That was much more than what economists were expecting, which was 1.8. And it's sort of like in the space of 1 minute, we went from thinking it's exactly 1.8 to thinking it's exactly 3.3. Which from a Bayesian perspective seems weird. Like if 1.8 is the mean of the prior and 3.3 is the observed value that goes into the likelihood, then what we should believe 831 when after it comes out, it should be somewhere in the middle. And it should be a probability distribution, not a single number, because we're not certain as to what the single number is. And then, a month later, second estimate comes out, and it's like, oh, no, it's 3.2. Well, and then, everybody shifts from thinking it was exactly 3.3 to thinking it's exactly 3.2 now. But 3.2 is not totally right either, and even if it was, we're not sure. So the way newspapers sound, we have this weird jumping from a particular number to another particular number. And that's what we believe, even though we have no real reason to think any one number is exactly right. Whereas from a Bayesian thing, you want to update this more gradually. And so if economists thought that it was going to be 1.8% originally, and then the data comes out to be 3.3 in the first release, it shouldn't be too much of a surprise that the second revised estimate is a little bit closer to 1.8. If, you know, the people who were forecasting it had some reasonable reason to believe 1.8 at a time, in which case 3.3 is maybe more likely to be an overestimate than an underestimate. That sort of thing. So Bayesian updating of a probability distribution makes sense. Leaping from one scalar to another without considering the big uncertainty in any of those scalars doesn't really make sense, even though that's what you see reported. All right. Questions about that first problem? Okay. And then second problem sort of introduces this idea of a measurement model, of which the first problem was a specific kind of that, and then talks a lot about how in the climate literature, you've got a lot of people who estimate or somehow come up with a distribution, oftentimes a normal distribution, for the observed value given the truth. And then, you know, acknowledging that there's some uncertainty, measurement error, in the quote-unquote observed value and how much it might deviate from the truth. So if we're talking about an estimate of what the average temperature was in dinosaur times, the dinosaurs didn't have any thermometers to measure what the temperature was. We're coming up with an educated guess of what the temperature was in dinosaur time based on like fossils and tree and other stuff that climate people and dinosaur people know about. But we don't know exactly what the temperature was, and we never will. We have an estimate. The estimate might be normal around the truth. But you have these sort of normal, often, distributions for observed values that deviate in some normal way from the truth, or they're assumed for it. And then climate people, like a lot of other scientists, reverse that around with scant justification into proceeding as if the truth is normally distributed around the data with the same standard deviation. And mathematically speaking, that makes no sense. And I think it's a consequence of, you know, they took like 1 or 2 classes when they were graduate students. They learned, or partially learned, something about frequentist inference. And with frequentist inference, you know, at least from a Bayesian perspective, but also from a perspective of any kind of normal person, everything looks backwards. You know, you're talking about the likelihood of, you know, the distribution normal for the data given the truth, but what we're trying to get at is the truth. And so you can understand the tendency to want to flip things around, you know, the right way up. But frequentist inference does not allow you to do that. And so you get into these conflicts where people do what they learned and then they just kind of massage it into something that makes sense in their heads, which is not what frequentist inference is about. Now, it is true sometimes that, okay, this makes no sense mathematically. And then if you ask the question, well, is there some prior distribution for which this thing that I did, which is completely backwards, actually turns out to be right? And sometimes, in this situation, yes, there is a prior distribution that could have been used for which the thing that seems backwards is actually the right way around. But to say, well, is there a prior for which what I'm saying is not completely nonsense? That's not really a prior. If you're like doing it after the fact and saying, okay, what prior would allow me to make sense of this? Because you're then choosing the prior after you've seen the data. So in a situation like this, the prior that allows you to just take this and make it into that is one where the prior cancels with the denominator. And that will often be a uniform prior over the truth. But what the article was implying, and I think they probably could have implied it in stronger terms, is that to say, okay, what prior allows me to flip the backward thing into the forward thing? That's a rationalization, not a justification. Right? Like, did you actually believe that your beliefs about the thing before you collected the data were uniform? If not, why would you be using implicitly using a uniform prior for this? Did your audience have uniform beliefs about the amount of global warming, that'll be in the next century or whatever? No. So why would you use a uniform prior on their behalf? Just so that you can take the frequentist thing that you did and make it into a Bayesian thing mathematically? When if that's what you wanted to do, you could have just done the Bayesian thing. Right? There's a good quote in there from someone named Maury or something like this, that this kind of dance that you see in the climate literature and a lot of other literatures, where they do some frequentist thing and then interpret it as a Bayesian thing, and that's only valid under a particular prior, is something to the effect of smuggling Bayesian inference in through the back door or something like that. But it's not something that needs to be smuggled. You could just do it if that's what you wanted to do. Unfortunately, the people who do climate stuff, like I said, they're graduates or were graduate students, probably were required to take like a class or two. That class or two was undoubtedly entirely frequentist inference instruction in a situation in which frequentist inference could not be less applicable. So nothing in the atmosphere is randomized. Moreover, we have observation. Well, we have one unit of observation. There's lots of different things that we could measure about Earth in different times or whatever. But we have a unit of observation, and our unit of observation was not a random sample from planets. So there's really nothing at all in climate science that has any bearing to the assumptions of frequentist inference. And yet, that's all they learn. And so it takes people like Anand and Hargraves to write a paper explaining very basic things about how what they're doing is not correct Bayesian stuff. So it is a bit alarming. Well, climate stuff is always a bit alarming, but it's even more alarming if you think about the fact that the people that we're counting on to save the planet can't even analyze the data correctly for the most part. So if we're fortunate enough to where politics in the United States and China and India and wherever else doesn't destroy the planet, it would be a real tragedy if the frequentists did. Like if technology evolves in a way that we can actually like keep global warming to a manageable level, but we screw it up because we can't estimate the things in a reasonable way, that would seem to be a very self-inflicted problem. But for the most part, the people who are doing this climate stuff, they know less about Bayesian estimation than you do. So with that in mind, you could do the rest of the problems. So one of the ones, they have some measurements of the numerator, measurements of the denominator. It comes out to be a fraction, looks something like this. Not totally symmetric. So heavier right tail than left tail. In theory, this actually goes into negative territory, even though we have no reason to think theoretically that like carbon dioxide and whatever could make the Earth cooler. But technically it extends out into negative territory a little bit, which doesn't quite make sense. You can get the distribution of the ratio looking at the thing on Wikipedia. It has a formula that when you write it out in code maybe is less intimidating than when you see it in math, but bottom line, it's non-negative, integrates to 1, then done it correctly, otherwise you haven't. And then, toward the end of it, they get into some posterior distribution stuff based on the same deal. Kind of looks like, it looks something like this. This is actually the one where we introduced uncertainty about lambda, the feedback thing. So that's part of what makes climate difficult. Okay, you release a lot of carbon dioxide or whatever into it, and then that affects the atmosphere, and then it keeps in more energy and then lets out less energy, and so that makes it warmer, and that keeps in more energy, and that, so it keeps feeding back on itself until it reaches the new equilibrium that is ostensibly this S value that we don't know, or at least we don't know now, because it's talking about something that's like 100 years in the future. But if you introduce a distribution on lambda, then you get something that has an even heavier tail and a shorter peak than the simpler thing they did in the paper, assuming lambda to be exactly 3.7. But we don't really know it's exactly 3.7 any more than we know that GDP growth last quarter was exactly 3.2 or anything else. Okay, so one point I wanted to make about this posterior PDF here that wasn't supposedly asked about in any of the problems. Some people would look at a PDF like this and say, well, we have a lot of uncertainty as to what S is. And that, in a manner, that is true. Based on the, not just this, but like the cumulative amount of scientific investigation around the equilibrium climate sensitivity, we have a lot of uncertainty as to what it is. So if we take, let's say, this magenta curve as like an accurate representation of our beliefs about what S is, even though it was only conditional on like a little bit of data. Some people would look at this and say, well, we don't know what S is, so we shouldn't do anything in the present that would be super costly because we don't even really know if the temperature is going to increase like a little bit or that much. So we should wait longer, maybe to collect more data, maybe we'll get a better idea of it in the future or whatever, and we can figure it out then. Which is not a good strategy, because by the time we reach an acceptable level of certainty as to what S is, it's going to be too late to do anything about what S is. So yeah, if we waited 99 years and then did this, we would probably get a more concentrated distribution, but then we would wish maybe that 99 years ago we had done more to reduce carbon dioxide emissions and stuff like that. So waiting for 99 years to find out what this is going to be in 100 years, not a great strategy. Also, people would look at this and say, well, the most likely value is slightly above 2. Our best guess as to what S is slightly above 2. So if we go with our best guess, maybe global warming is not that big a deal. I mean, it would probably have some effect if the Earth were to increase 2 degrees temperature on average, but we might be able to manage that. But that is inconsistent with what we have learned about decision theory, which is not based on the mode, but based on the expected utility. So if you take this distribution of S and put it into the cost function, or estimated cost function or whatever, as to how much cost and damage it's going to be depending on how much the temperature increases, and let's say that's your utility function, or the net of that is your utility function, something like that, and then you take the expectation of that, then you would be in a position to use decision theory. And even though we didn't exactly do it in this assignment, if you put this into a reasonable cost curve that people have, or function that people have estimated, and take the expectation of it, the expected cost of global warming, if this is our beliefs about what global warming will turn out to be, is in the quadrillions of dollars. And that's because this right tail is pretty heavy. So if you just look, okay, what's the chance the increase in temperature is going to be above 4 degrees? That might be, between 10 and 15%. Something like that. Now, if you put this into the cost function and then weight it by the probability of these things happening, if you're putting a 15% weight on the cost of global warming, if the amount of global warming is greater than 4 degrees, then that's just a disaster. Like, most of the big parts of the Earth would be uninhabitable if they were 4 degrees warmer. Like, all of our agriculture would be messed up. Antarctica would melt. Islands would all get there would be no Columbia situation. So the cost of that, even though it has only like a 15% chance, you're putting like a 15% chance on thousands of trillions of dollars of cost. So the expected cost of that could easily be in the hundreds of trillions of dollars. And so if the expected cost of like not doing anything is in the hundreds of trillions of dollars, would you be willing to pay $1 trillion a year for the next 100 years to reduce carbon dioxide and stuff like that in order to avoid or reduce the chance of having a huge amount of cost due to high temperatures? Yes. Under decision theory, you'd be willing to pay $1 trillion a year if the expected cost of not doing so was hundreds of trillions of dollars, depending on how much you discount the future, and so forth. But that's not the sort of analysis that you will usually see. It'll be like, we don't know what S is, so we should wait until later to do something about it. Or S is most likely not that bad. Instead of saying, well, if this is what we believe about S, in expectation, the costs of that are just astronomical. And that is the strongest case that can be made for taking expensive action now in terms of, you know, making cars and planes that be electric and all kinds of other stuff like that, to reduce emissions. Okay, so last bit, what would Fisher think about all this? What would you come up with? Or what all did you say about that?
Yeah, I said that he would probably mostly disagree for the most part, just because he's strongly frequentist and he would have relied a lot more on the p-values and statistical inference and all the hypothesis testing. But I said that he would appreciate maybe a different approach in trying to focus on doing all these statistical tests to get the evidence that they need. But I said for the most part, he disagreed.
Yeah, I don't think you'd appreciate it that much.
Yeah.
So again, this is maybe not the fairest thing to put words in anyone's mouth, much less someone who is dead. But before he was dead, he had a lot to say about science. Again, we're talking about plants mostly. But if he had said the same thing about climate change that he said about agricultural experiments, it would have to be, in order to be objective about this, here's what you need to do. You need to take a bunch of planets that are similar to the Earth, take randomly half of them to be treatment group and randomly half of them to be control group. In the treatment group, over the span of a couple hundred years, double the amount of carbon dioxide in them, wait a couple hundred more years, see how much the temperature rose in the treatment planets as compared to the control planets, take the difference between those, that would be your estimate of the average treatment effect of doubling the carbon dioxide, and then maybe do a test of the null hypothesis that there's no difference in temperature between the treated planets and the control planets. And obviously that's unfeasible. And a completely unhelpful recommendation as to how science should proceed. But moreover, Fisher said, well, if you can't be objective about stuff, then you shouldn't say anything about it at all. So no priors and putting distributions on things that are not random variables and stuff like this. And so Fisher would say, if he were consistent, that all this climate stuff, the climate science, done by climate scientists, is not right, not a basis for action. It's not good science. And Fisher legitimately did say stuff like that with regard to the tobacco industry, which he was a lobbyist for many years, up until he died from lung cancer, insisting that the science that people were doing as to the prevalence of lung cancer among people who were smokers was not like objective or well-grounded science. They couldn't really do actual experiments on, people, and so they did not have, to Fisher's standards, objective evidence that smoking caused lung cancer. And he would say the same thing, that climate scientists don't and cannot have objective evidence that carbon dioxide causes global warming. And if we can't say that objectively, we can't say it at all. That's like the real problematic statement. So this is one of many examples that we can come up with what scientists are desperately trying to do. Fisher says is not appropriate for science. And that's one of the big reasons why Fisher's view has been so pervasive in textbooks and whatnot, social science, climate science, lots of other fields, which seems, lots of examples where we can come up with where Fisher is in opposition to the scientists, not like providing a practical way for them to do the science that they want to do, the questions that they want to ask, that sort of thing. Anything more? Question? Okay. Still got this. Start that. All right. So this week we're going to talk about linear models, in particular with the rstanarm R package. So this, for the first time, actually is somewhat relevant in that I did write half of the rstanarm package along with the former QMSS student, Jonah Gabry. So as we said last time, the Hamiltonian MCMC algorithm in STAN, it only requires us to have the logarithm of Bayes' rule, and any constant is not going to matter. So constant being anything that doesn't depend on theta, namely the denominator piece. So that's why we just wrote the proportion sign here, just basically says this is correct up to a constant. So we have the logarithm of the prior PDF and the logarithm of the likelihood of the parameters theta, which is to be evaluated at the observed y that we have. And with that, Stan can do Hamiltonian MCMC to get draws from the conditional distribution of theta given y. And as we said last time, Bayesians can, doesn't mean they should, doesn't mean they have to, can use the same log likelihood functions as frequencies. In which case, if you have the capability to maximize the log likelihood function to obtain a point estimate of theta, then it's not too much harder to specify priors on the elements of the parameters, then use stan to obtain lots and lots of draws, which are really good from the posterior distribution of theta given y, giving you a function estimate of theta, a probability distribution for theta given y, rather than merely a point estimate of theta. So a much richer answer. And the rstanarm package, which we're going to start talking about today, was talked about in the reading, uses the same syntax and likelihood functions as more famous R packages have, but adds priors. Those priors are going to have default values, which you shouldn't really use, but they're there. And then is going to pass it all to the Hamiltonian MCMC algorithm and stan to get draws back from this posterior distribution rather than using optimization to obtain the value of theta that maximizes the log likelihood. So it's going to be based on this, not merely this, but more importantly, it's not finding an optimum, it's taking draws from a distribution. It's a very different mathematical apparatus for estimating. So if you pull from GitHub, switch your working directory to week 7, there should be a file called macroeconomicdata.r, which if you source it, will bring in essentially the same data that we had for homework 2. The only thing I added was the unemployment rate for each quarter, and then I constructed the variable x to be the quarterly change in the unemployment rate, and that gets us into something known as Oken's law, which postulated a linear relationship between economic growth in a quarter and the change in the unemployment rate during that quarter. And there's some theoretical reasons why that makes sense, but intuitively speaking, if the economy is like growing a lot, then there should probably be less unemployment. And if a lot of people are getting laid off or fired or whatever, then probably the economy is not going to be doing so good. So it kind of makes some intuitive sense, and since it's named Oken's law, it's probably not super inconsistent with the data. So here is a notation for so-called generative models that was introduced in the McElreath reading. This stuff that we see on the left. And by convention, we start reading at the top and go to the bottom, which is the convention for how anyone reads. But the convention is to start with the data. And so when you see each of these things, they sort of end with the statement where, and then you go on to the next line. So this first thing means for all n here is like quarters of time. The outcome in quarter n, which is the economic growth rate, is defined as the expected economic growth rate in quarter n plus an error for quarter n. Where, for all n, the errors are drawn from a normal distribution with expectation 0 and standard deviation sigma. Okay, what's sigma? We'll get to that. Where the expectation in quarter n for all quarters is defined as alpha plus beta times x for that quarter, where x in this case is the change in the unemployment rate. Okay, so epsilon is kind of defined. We haven't said anything about what sigma is yet. Mu is kind of defined, but we haven't said what alpha and beta are yet. Okay, where sigma is drawn from a, let's say, exponential prior with rate r. So exponential is a special case of gamma. We talked a little bit about the gamma distribution on homework 1. If you take a gamma and make the shape be 1, that specializes to an exponential with rate whatever. So r here is the rate parameter. The thing to remember about that is the expectation of an exponential distribution is the reciprocal of the rate. So if you think about what your expectation for sigma is, and just take the reciprocal of that, that gives you R. So my convention, but I think Richard's convention as well, is to use Greek letters for unknowns and American letters for known values. So this is, the unknown sigma has exponential prior with expectation 1 over R. And I'm going to say what R is under my prior. Moreover, alpha has a normal distribution with expectation M alpha and standard deviation S alpha. Choose values for M and S. And beta is going to have a normal distribution with expectation M beta and standard deviation S beta. Also have to choose values for those. So I got to choose 1, 2, 3, 4, 5 scalar constants. And then I can draw from this generative model. So we read it from the top to the bottom, but when we code it, we start at the bottom and then we go to the top. Okay. So if we go over here and look at the code, let's say we want to draw 10,000 times from this, okay? Beta prior on, or the normal prior on beta. So as the unemployment rate goes up, we think economic growth more likely to go down. So the expectation of it is negative, but we're certainly not too certain about what it is. But it can't be super huge. Like it can't be greater than negative 100. Like if the unemployment rate went up by 1, the economy would decrease by 100%. That makes no sense. So it can't be too huge. Similarly with alpha, well, alpha we can interpret as the expected value of y if x is 0. And so the average change in unemployment basically is 0. So this would be sort of expected value of y when x is 0. Normally economic growth is like a little bit positive, as we saw it tends to be between 2 and 3%. So, you know, we could have a normal prior around that with a center of 3 or so. And then sigma, we put in exponential prior, draws from exponential distribution with a rate of 0.5, meaning an expectation of 2. So all those are somewhat reasonable. And before we go on to predictions, I want to make an important point. So mathematically speaking, like if you substitute, or you just look at mu basically here, okay. This is the equation for a line. And a line, it's valid as a line for any real numbers alpha and beta. Anywhere in the real plane. Any alpha and beta yield you a line if you do alpha plus beta times x. It's going to have a slope of beta, intercept of alpha. Okay? Mathematically speaking, that's all fine. However, scientifically speaking, there are very few possible values of alpha and beta that yield a substantively useful line for social science purposes in this context, predicting economic growth. Very few values of alpha and beta would be substantively reasonable. And so a Bayesian perspective on the process of choosing priors is basically to say, okay, this is mathematically valid for any value of alpha and beta. But it's not scientifically valid except for reasonable values of alpha and beta, reasonable scientific values of alpha and beta. And so it's incumbent on the scientist to state in advance what they think reasonable values of alpha and beta are, in order to define scientifically useful lines. And so from that perspective, choosing a prior is just the responsibility of the scientist. You need to say what's reasonable beforehand, not after the fact. And you need to phrase this in terms of probability distribution. It's not like something is or is not reasonable, but we have degrees of reasonableness that are quantified by that. And then once we have like 10,000 realizations from our prior, we can cross-join it with the data set that got downloaded when you did source macroeconomic data from Fred. And the cross-join function in the dplyr package is going to make a copy of each of the 10,000 rows of priors. And for each of the 300-ish rows of data, it's going to copy all of priors in. So this predictions thing is going to be like 300-ish times 10,000. The number of rows that it has. And then we're going to construct mu, because data has x in it, and alpha and beta came from priors. So we're going to construct mu as alpha plus beta times x. We're going to draw epsilon from a normal distribution with expectation 0 using our realizations of sigma, 10,000 different ones. And then add mu and epsilon to get our prediction for y under the prior predictive distribution. All right. So this process we're going to do a lot. So you need to be familiar with it, both the mathematical way of stating the assumptions and then reversing the order of it to do drawing from the prior predictive distribution in R. But it is really similar to what we were doing with bowling all along, or at least bowling once we had the ability parameter in there, in terms of drawing from all these distributions to get predictions of the observables. In this case, it's y rather than bowling pins, but whatever the outcome may be, this is how we would simulate from it under a linear model. Moreover, it should be noted that frequentist simulations look a lot the same. They wouldn't do this part. Rather than making beta, alpha, and sigma be draws from a distribution, they would set them to constants and then do this part here to get predictions of y given constant values of alpha, beta, and sigma. And so that seems like the bottom half of what we've done here. But moreover, like if you set beta, alpha, and sigma to particular constants, how do we know those are the right constants? We don't. We're just asserting those. So using distributions that reflect our uncertainty before we see the data on these things is, I think, quite plausibly a more realistic way to proceed, in which case our predictions for y are going to have even more uncertainty in them because we're uncertain about alpha, beta, and sigma, in addition to being uncertain about epsilon. So we got all that. Once we have prior predictions for y, we can plot them, do other sorts of analysis on them to see if they make sense. And as I alluded to before, we'll get into more of it after spring break. One way to check whether your prior distributions for the parameters make sense is to see if those prior distributions for the parameters imply a reasonable predictive distribution for the observables. And in this case, I would argue we're looking pretty good in terms of what we would typically expect growth to be. You know, maybe 15-20% chance that it's negative. Okay, that happens sometimes. Rarely more than 10. So for a country like the United States, that would be a very rare situation. Mostly in the 2 to 3 range. Okay, so this is looking okay. In which case my priors for alpha and beta and sigma could not have been that bad. Could write a STAN program, like I said, in this class, we're not going to do that, but it would be relatively straightforward. We could write this in R. So this is kind of similar to one of the things that we did on the homework. We're going to write the numerator of Bayes' rule in log form. So it'd be a function of alpha, beta, and sigma. And then it would depend on all these constant values, x and y, and the m and the s for all the things. So we would use the exponential density, or really the logarithm of it, with rate r sigma, and then normal density for beta and alpha, and normal likelihood, log likelihood, for really this, which is our expression for the expectation of y, evaluated at the observed y, and the purported sigma in log terms. Since the likelihood is assumed to be the product of conditionally independent values, the natural logarithm converts that to a sum of logarithms. So we just put all this in the sum function, add it all up, and we have the numerator of Bayes' rule in the R function. Stan is a bit more clever in that it can actually get the derivative of all this with respect to alpha and beta and sigma, and it needs the derivative in order for it to do the physics with the velocity and stuff like that under the Hamiltonian thing. But then it can move around this parameter space of alpha, beta, and sigma, getting draws from all of those things. And that brings us to the stan GLM function in the rstanarm package. So it does multiple Markov chains, 4 by default, in which case you'd be well advised to do those in parallel using the 2 to 4 cores that you presumably have on your laptop with this line here, line number 2. And then in order to execute this, we call this stan underscore GLM function, whose syntax is deliberately chosen to be compatible with the GLM syntax that comes with R. So we're going to specify this formula here where our outcome, growth in GDO, so basically the average of GDP and GDI, depends on the change in the quarterly unemployment rate. Given the data set, we need to pass Stan a random number seed in order to make this replicatable on your machine. Stan uses a different random number generator than what R uses, and so merely calling set seed outside of this is not sufficient to make Stan deterministic. You also need to pass a seed to Stan, in which case every time you do it on your laptop, it'll come out the same. Stan GLM adds additional arguments above and beyond what's in GLM, specifically prior intercept, which it could do what we did before. Prior, which is going to be on the coefficient, -2, 1, its parameters. And then prior underscore aux is for the auxiliary variable, which in the case of a linear model is sigma, the standard deviation of the errors. So I'm going to give that an exponential prior with a rate of 0.5, which is to say an expectation of 2. So let's have everybody write down those lines after having sourced macroeconomic data from the week 7 folder.
I'm getting an error for the plot.
Okay, we'll worry about the plot in a second.
Oh, okay.
Did you manage to get 4,000 draws?
We only have 2,000.
Some number of draws? Okay,
Yeah.
that's fine.
We have 2,000 iterations.
Okay. Everybody else caught up? No?
Sorry, could you show the source code again?
It's just source.macroeconomicdata.r. But you have to change your working directory to week 7 after you pull. There's only one file there, so just source it. And that will create the data set. Okay, while people are still catching up with that, I want to emphasize that calling this is scarcely more difficult than calling GLM. Yes, there's an additional thing about your priors about the parameters, but one, I argued just before, that's really the scientist's responsibility to say what are reasonable values of parameters in advance. Moreover, even if the scientist abdicates their responsibility and just does the first line here, there are default values for prior, intercept, prior, and prior ops, which are not optimal, but they will allow this thing to work. So really, if we just talk about the first line, calling it is really no more difficult than calling GLM. But we get a much richer answer by doing stan GLM rather than doing regular GLM, which only gives us point estimates. And broader point, learning how to do something is often not terribly difficult once you know what it is you're doing and why it is you're doing it. So we focused a lot on the first 6 weeks about what Bayesian inference is, why we would want to do Bayesian inference rather than frequentist inference, and we'll get into supervised learning after the spring break. So we've talked a lot about what it is and why we want to do it. Now we're starting to get a little bit into how, but how is not terribly hard if you have a good foundation of what and why. But a lot of classes just immediately start with how, in which case you get confusion like we saw in the homework about people getting like a likelihood confused with a posterior and stuff. So anyway, hopefully everybody's managed to get something by now. You can plot it, and the good thing about these plots is like the answer is these probability distributions of function. And these functions have PDFs. And so if you look at the plots, that sort of gives you a better perspective on the whole thing than to focus on a particular number such as the mode, which, as I said before, the mode is not very important to a Bayesian. It's just one point out of an infinite number of points. Like, the important thing is the function. Yes, the function has various properties, such as a mode, a median, a variance, whatever. But like, we can just plot the function, and that's kind of the answer. That is the answer. But there are aspects of the answer that can be quantified more. If you just print out the result of post, should get something essentially like this, maybe randomly different a little bit, but basically the same thing. Good? Okay. Where it clearly labels this as the median of the posterior draws. So the median of the posterior draws for the intercept, this thing, I was pointing to the wrong thing, that's the intercept. This is the coefficient on x, and that's the standard deviation of the errors. So the median of alpha in what posterior that we had before is 2.8. An estimator of the standard deviation of these things is given to the right. It's not actually the same estimator of the standard deviation that you're familiar with. It is one that is more robust to outliers in the tails. But anyway, it is a estimator of the standard deviation, and it is 0.2. So our posteriors are fairly precisely estimated. It's the same for the coefficient on x, although it has a median posterior draw of negative 4.2, and the median of posterior of sigma is 2.5. And so having conditioned on 214 quarters worth of data, we've updated our prior beliefs into these posterior beliefs, and these posterior distributions have medians, they have standard deviations. We can talk about what those things are. Now, unfortunately, well, one, deliberately, we chose the print output to be similar in structure to the print output of a GLM object. It has less going on here because we don't do like tests of a null hypothesis as 0 and p-values or whatever, but because this is kind of like the first step that people often do after they call stand GLM, and it looks kind of the same as what GLM looks like, there is an unfortunate tendency to interpret these things as the point estimates. And they're not the point estimates. They are the medians of a function, of a probability random variable. And so they're not the mode, they're not the mean, they're the median. You can calculate a mean, but it doesn't do that here. But none of those things are a point estimate, really. In the same sense, a maximum likelihood estimate is the value that makes the likelihood the highest, etc. So even though these are numbers, we want to interpret them as summaries of random variables rather than points. Unfortunately, people look at the output of GLM and imagine it to be a summary of random variables because they confuse frequentist with Bayesian, even though Fisher created maximum likelihood estimation to destroy Bayesian estimation before it could take root in science, even though Bayesian estimation was pretty much unfeasible in the 1920s, except in situations where we had conjugacy. So these are not the point estimates. Moreover, we can call the posterior interval function on the object that's created and specify some level to give us quantiles of the draws. So 5% of the draws for the coefficient on x are less than negative 4.55, and 5% of the draws are greater than negative 3.83, etc. Same thing for sigma and for the intercept alpha. And so these are what Bayesians call credible intervals, but they are not confidence intervals. These are what confidence intervals are mistaken for. So when Chersey Neyman said, like we talked about a couple of weeks ago, oftentimes people, they take a 95% confidence interval, they think, okay, there's a 95% chance that the true parameter is between here and there. Neyman explains why that was obviously wrong, and Neyman is correct, and all the people who are doing whatever it is they're doing are obviously incorrect. But the obviously incorrect interpretation of a frequentist confidence interval is the entirely reasonable, correct interpretation of a Bayesian credible interval. We change the estimator from a Neyman thing to a Bayesian thing, and now we're like not upside down. These are not confidence intervals, although you will hear them referred to as confidence intervals, or you will see people use the abbreviation CI for both a confidence interval and a credible interval without distinguishing what they are. Questions?
That's a simple question, but how do you interpret the intervals and the credible intervals?
So there is a 90% chance under our model, inclusive of the priors, because the priors influence the posterior. There is a 95%, or 90 in this case, percent chance that the coefficient on x is between negative 4.55 and negative 3.83. So, or you could just kind of see from the plot, there's no way it's anywhere near 0, much less positive. Which makes sense. But given the data which updates our priors, we now have pretty specific beliefs about all this stuff. We do not have confidence intervals. Moreover, you can call the asDataFrame function on post and get a data frame of like 4,000 draws that you can do anything you want with. It's like we've been doing for bowling, or the vaccine thing, or the homeworks, whatever. So if you have a hypothesis, and you want to evaluate the posterior probability of the hypothesis being true, we can calculate the probability that x is great, or the coefficient on x is greater than negative 4, which comes out to be 0.18. So 18% of the draws entailed a beta realization greater than negative 4. This is not a p-value for the null hypothesis that beta is exactly equal to negative 4. It's a probability. It's kind of small. P-values are probabilities. P-values are often kind of small. That does not mean this is a p-value. That does not mean a p-value is a substitute for this. This is what it says it is. Proportion of draws that were of beta that were greater than negative 4. And a p-value has a great history of being misinterpreted because it's the probability of observing data more extreme than this, given that the null hypothesis is true, which from a Bayesian perspective or any sort of human perspective seems like a backwards way of approaching the question. Yes?
So basically, with this probability value that you have, like this 0.18, would it be like if we were interpreting it like frequentist way, we would basically say we failed to reject it, essentially, right?
We would not interpret this the frequentist way.
Oh, no, I'm just asking, like if it was a frequentist, is like...
If it was a p-value, and we did maximum likelihood, and we had a null hypothesis of negative 4, then conventional speaking, we would fail to reject the null hypothesis that is negative 4.
Okay.
But this is nothing like that. Even though that p-value stuff is often confused for what this is.
Mm-hmm.
So what this is fairly straightforward. And if you didn't have to worry about what a p-value is, you'd be fine. This is like one line of code. How can you get confused about that? Whereas, like, over 90% of people are confused about what a p-value is. For good reason. So if we wanted to predict growth in the fourth quarter of 2023, we could just take the last value of our data. So the unemployment rate didn't change very much, but it went up like a little bit. Take all the draws of the intercept, that's alpha, add them to x multiplied by all the draws of x that we got from the posterior distribution. Add to it a realization for the errors, which have an expectation of 0 and a standard deviation being the posterior realization of sigma. And then we can plot a distribution of predictions. This has a lot of uncertainty to it. So this is not conditional on yesterday's release of the GDP. because GDO hasn't come out yet, and this model that we estimate was on GDO, whatever. So if Wednesday hadn't happened, this would be our beliefs about the predictions for mu, the true amount of economic growth in the last quarter of 2023, conditional on the unemployment rate only, not conditional on the released estimates of GDP and GDI. Released estimate of GDI won't come out until March. Okay. Anyway, distribution of predictions. Fairly wide. A lot of legitimate uncertainty as to what the truth is if we only condition on the unemployment rate. Unemployment rate provides some information about the truth, but not nearly sufficient to be absolutely certain as to what the truth is. Even under Oken's law. So Art Oken did not call this thing Oken's law. Oken's friends called this Oken's law. Better description of it would be a rough empirical regularity that Art Oken, among other people, discovered mostly holds for the United States for most of its history, on which we could collect data, but differs somewhat in the post-pandemic times, and it differs somewhat from one country to the next. But Oken's law is a much more succinct, although not necessarily faithful, description of that empirical regularity at issue of it. Moreover, you don't actually have to form these predictions yourself by pulling out the draws and then doing basically this here, but with the posterior draws rather than the prior draws, or really like this, except you use posterior here to make the predictions, because the rstanarm package includes a posterior underscore predict function that takes in the posterior objects produced by stanGLM and a data frame, which can be the same as the original data frame, or it can be a new data frame, so to predict something that hasn't happened yet, such as the fourth quarter GDO release. So we call posterior predict. We're going to get a matrix back. It's going to have 4,000 rows, one for each draw, and one column for every row in new data. In this case, we just had one row. We're only interested in the fourth quarter of 2023, but we could predict it for the first quarter of 2024. Well, the first quarter of 2024 is not over yet, but as soon as it is, we could predict it. Etc. So we only had one row in this case. It's only going to have one column, but it's going to have 4,000 rows, which are draws from this predictive distribution, particularly the posterior predictive distribution, conditional on the past data. So we can use that. Its semantics are similar to the predict function that's already in R, but we have to put the posterior on it to indicate these are draws rather than point predictions. Consequently, there's 4,000 of them rather than just one. They encapsulate our uncertainty about the predictions, which in this case is considerable and would be completely swept under the rug if we just had a point estimate and 1 point prediction rather than a whole distribution. So we got that. We saw a little bit yesterday in the recitation session how you can use the ShinyStan web app and click around. It works with objects created by rstanarm. You can make a whole lot of plots. You can save those. But all of the plots that can be made by ShinyStan can also be created or recreated with R code. So for example, if we wanted to do a posterior predictive check, so this is going to produce the plot on this slide here. So the kind of blue, light blue, oh well, there's two kinds of light blue. The darker light blue lines are 50% predictive intervals. The lighter light blue lines are 90%, I think. You can customize that. And then the blue dots are the actual data. And this is ordered by time here. So why the dark blue dots, those are actual data. And then the different kinds of blue and gray are parts of the posterior predictive distribution for past data. And so an entirely reasonable Bayesian interpretation is that 90% of the dark blue dots should fall in the light blue intervals if the model were correct. And as we can see, that might actually kind of be the case. There's certainly some exceptions where the blue dot is outside of the predictive interval, but that looks to be, 10%, maybe less, whatever. Over here, 200 quarters since the start of 1970 was 2020. And so we can see we have a fairly bad miss here when the actual reduction in growth was like 30%. The model would have predicted somewhere around 40%. This is the second quarter of 2020 when almost everything was in lockdown in the United States. This is the quarter right after it, the third quarter of 2020, where the lockdown was mostly lifted or people did like remote work or, over Zoom or whatever. And consequently, we got much higher percent economic growth than that was predicted by the model. So it's kind of debatable as to whether we should be using 2020 data, because Art Oken certainly was not developing a model that was intended to explain, economic performance during aberrations such as a pandemic. The only pandemic that was remotely comparable was the one in 1918 or something like that, and we didn't really have economic data at the quarterly level back then in the first place. So, but all that said, actually, this is not horrible predictions considering how extreme of a situation we're dealing with. Okay, so another famous study, and the data set actually is included as an example in the rstanarm package, comes from some child development thing where the principal investigators got a whole bunch of money to administer IQ tests to 3-year-olds to see how smart they are. And we could think about a model for the score of the 3-year-old on the IQ test as a function of various characteristics of the 3-year-old's mother. When doing so, I like to change the units of a lot of these variables, dividing them by 10 in this case. So thinking about age is measured in decades rather than in years, and IQ similarly in 10-point variable increments rather than 1 point. But that's just a scaling. In principle, we could get on without that. But we're going to set up a similar linear model, but now we have multiple predictors. So y for the nth 3-year-old is defined as systematic value eta plus an error. Error is for each of these normal with expectation 0, standard deviation sigma, where eta is defined as alpha plus a coefficient on whether the mother graduated from high school, plus a coefficient on the mother's IQ, plus a coefficient on the age of the mother when the 3-year-old was born. So like 3 years in the past. We're going to define alpha as mu minus coefficients multiplied by the average values of each of these things. And you can see if you substitute this alpha for that alpha, and then factor out the betas, then the betas and the mu would be relative to so-called centered predictors, which is the default in rstanarm, and it's usually a good thing to do. So without this, like beta 3 would be the coefficient on the age of the mother for a mother who was 0 years old, which is not even biologically possible. So by centering the variables or making the parameters relative to centered variables, now we're interpreting beta 3 as the coefficient on age relative to the average age of the mothers in this data set, which is a well-defined like biological thing. So in rstanarm, we're actually going to put the prior on mu. Mu would be the expectation of y if all the variables were average, rather than the expectation of y if all the variables were 0. So we have an exponential prior on sigma, normal prior on mu, normal priors on the betas. So real quick here, because we're already running out of time, what do you think would be a reasonable value for m sub o, the prior expectation for mu, if mu is the expectation of the 3-year-old's IQ for a mother who was average?
120.
120. What would you say that?
Is that around the average IQ score that people usually get?
So the average is actually 100. Right. So IQ test is constructed to have an expectation of 100. Moreover, IQ test is constructed to have a standard deviation of
15.
15. So a halfway reasonable prior for sigma would have an expectation 1 over 15. But that would be actually assuming like all the betas are 0. Like the high school and the IQ of the mother and the age of the mother have no influence at all on the IQ of the 3-year-old. So that might be a bit pessimistic. Maybe we would use for R like 1 over 10, which is to say the conditional error is a little bit less than the marginal error. Something like that. And you could choose halfway reasonable values of the coefficients as well, which is what we do here. So call stan GLM with the kid's IQ as the outcome variable, whether the mom graduated from high school, the mother's IQ, and the age of the mother when the child was born, given the data set. Here I'm going to specify prior PD equal true, and this tells stan GLM not to condition on the outcome. And if you don't condition on the outcome, you're just drawing from the prior. Stan can do that. Prior on the intercept, namely mu, I'm going to say 100 and expectation 100, standard deviation 10, based on what I know about the construction of IQ tests. Some prior coefficient values on the coefficients, those are normal, and yeah, like expectation of 10 on sigma, something like that. So I can construct some seemingly reasonable priors. I can check that by calling the posterior predict function on the draws from the prior. So this is not actually posterior, this is just prior predictions if I didn't condition on the outcomes, or posterior prediction conditional on nothing. But anyway, I can use that to get a matrix of prior predictions, and I can plot their prior density of it, see if this looks reasonable, which I would say it does. And hopefully one thing that you can take away from this is that if you can get a halfway, not even halfway, like minimally reasonable prior on mu, the intercept in a linear model, relative to centered predictors, which we can in this case, but honestly in a lot of other cases. If you just think about what you anticipate the outcome to look like, if you can get a minimally reasonable prior on the intercept, your prior predictions are usually going to come out fine. And when you condition on the data, Stan is going to work really well. So people a lot of times think, well, choosing priors is really hard, it's really subjective, all this sort of stuff. But if you get a little bit of practice, and if you know enough about the outcome to be specifying some sort of model about it, you should know enough about the coefficients and other parameters to specify some minimally reasonable prior distributions on those, which gets you closer, and then it makes it easier for Stan to get you draws that are really good from the posterior distribution once you do condition on the data. So this is draws from the prior predicted distribution. I'm ready to go. I can call the update function on the prior object, changing the argument prior BD to false. So now I'm going to condition on the outcome data that I observe. I get posterior draws. Now the thing that is a little bit confusing, in the posterior draws, this intercept thing corresponds to alpha, not to mu. This is for compatibility with GLM. Probably I would have done it my way if I didn't have to resemble GLM, but I do. So intercept here is the posterior of alpha, even though you specified the prior on mu relative to centered predictors. The posterior doesn't have mu in it explicitly. The posterior has draws of alpha and beta. There, okay. But anyway, we conditioned on 434 observations. We get, posterior medians. I could plot them, stuff like this. Posterior sigma had a median of 18, so actually bigger than what we thought. But anyway, so one thing to take away here, if you look at the coefficient of age, it has a median of 1 and a standard deviation of 2.1, which if we were to take a frequentist perspective on this totally not frequentist thing, you might say to yourself, or other people might say to you, well, mom age is statistically insignificant. It's not over 2 standard errors away from 0. Ergo, it's 0. Ergo, let's take it out of the model. None of that makes sense from Bayesian's perspective. Doesn't even make sense from a frequentist perspective. But it certainly does not make sense from a Bayesian perspective. From a Bayesian perspective, we can say we're rather sure that the effect of mom age is rather small. We're not at all certain about it. It's more likely to be positive than negative, but we can't rule out the possibility that it's negative. But we're not taking it out of the model because we have no strong evidence that this is exactly 0. We have evidence that it's around 0, but maybe more likely to be on the positive side of 0 than the negative side of 0. Right? So there is no statistical significance because there is no testing of a point null hypothesis, because why even bother? The probability that a real number is like a real random variable is exactly 0 is nothing to begin with. Okay. Not going to do that one. Time check. Almost out of time. Okay, so there's some stuff. I put in a model with interactions. You can do that using the same syntax as before. It's talked a little bit about in McElreath. What I do want to say is that there's a separate stan-ln function in rstanarm that also estimates linear models, but it uses a different prior. So you still have prior on the intercept, but stanLM allows you to put a prior on the R squared. It's actually a beta prior on the R squared, or the center of the beta distribution prior on the R squared, which kind of gives you a joint prior on sigma and the betas collectively. So rather than specifying priors that are independent of the coefficients one by one, you can put a beta prior on the R squared, which gives prior information both about the coefficients collectively and sigma, which is extraordinarily useful if you have a lot of coefficients and your beliefs about them are not independent of each other, which they shouldn't be independent of each other. Moreover, it can be shown that this prior is the maximum entropy prior, so it has the least amount of information about the coefficients for a given expected log R squared. So if you were to specify an expected log R squared, this has the most uncertainty conditional on that. So you need to say what your prior beliefs about what the R squared is. And in the case of IQ of 3-year-olds, you should not be that optimistic that you can explain all of the variation in the IQ test of 3-year-olds with anything, much less like a few things about the 3-year-old's mother. Because if you've talked to a 3-year-old recently, they have a lot of variation from minute to minute. So the idea that we could explain all the variation in their performance on an IQ test that they can't even understand is preposterous. So you should have prior beliefs about the R squared on the low side here. And you actually get a posterior distribution back on the R squared, which is also on the low side, confirming what it is you thought you knew about 3-year-olds. All right, so midterm is happening next week, this time. So almost 2-hour exam. It will cover everything, including what we did today. So with rstanarm and linear models. It'll be like a homework, so at the end of it, you'll need to upload a .qmd file and a .pdf file. We will have recitation and office hours as usual next week, Tuesday and Wednesday. And you can certainly ask questions on a discussion up until the exam starts. And you can use any of the class material for the exam. So bring your laptops definitely, but also make sure you've got all the notes and stuff like that pulled in case there's like flakiness of the internet connection or whatever. Make sure you've got the readings and all that. Questions? Okay, well, if they come up, and they will, put them on ed discussion